Trigonometric functions of acute angles. SOH-CAH-TOA. What does that mean? Well, SOH-CAH-TOA is a helpful mnemonic for remembering the definitions of the trigonometric functions for sine, cosine, and tangent. So we have to have a right triangle, and we have to choose one of the non-right angles to focus on. So here I've chosen this to be my angle theta, and we want to understand the side lengths of the right triangle in relation to this particular angle theta. So the side length that is always opposite the 90-degree angle, the longest side length, is called the hypotenuse. Then in relation to my angle theta, the side directly across from it is called the opposite side, leaving the side right next to it called the adjacent side. So when we want to think about sine of theta is defined as the opposite side length over the hypotenuse. That is where the SOH of SOH-CAH-TOA comes from. Then we're going to go ahead and look at the middle part. So we have cosine of our angle theta is adjacent over hypotenuse. So for this angle theta, I would look at the length of the adjacent side over the length of the hypotenuse. And then finally, tangent of theta is the opposite side over the adjacent side. So tangent is equal to the opposite side length over the adjacent side length. So SOH-CAH-TOA is coming from sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. In this example, we want to find the sine, cosine, and tangent for angle theta. So here's my angle theta inside of my right triangle, and I have two side lengths given, 6 and 11, the opposite side and the adjacent side. But I'm actually missing the hypotenuse. So I'm going to have to solve for that using the Pythagorean theorem. So I'm going to go ahead and call that side length z, and go ahead and do that work off to the side. So 6 squared plus 11 squared has to equal z squared, or 36 plus 121 equals z squared. So 157 equals z squared. So z is plus or minus the square root of 157. But we're going to only take the positive value because we're talking about the side length. So z, the hypotenuse, is the square root of 157. So now I have my opposite side 6, my adjacent side 11, and my hypotenuse, the square root of 157. So sine of theta is equal to opposite 6 over hypotenuse square root of 157. And if I rationalize, I get 6 times the square root of 157 over 157. And now cosine theta is equal to adjacent over hypotenuse. The CAH in SOH-CAH-TOA, adjacent is 11 over the square root of 157. Again, rationalizing, I get 11 radical 157 over 157. And finally, tangent is the TOA part of SOH-CAH-TOA. So opposite over adjacent is just going to give me 6 over 11. So tangent theta is equal to 6 over 11. Defining the trigonometric functions. So now we're going to make a connection. We're going to let theta be an acute angle in standard position with xy, the point on the terminal side of that angle, on the circle with radius r, so that x squared plus y squared equals r squared. That was a mouthful. Here's what's happening. So on this image, I have here is my angle theta, and xy over here is a point that's on the terminal side, and it intersects this circle here, and this circle has a radius r. So we can see that we have a right triangle formed here with that interior angle theta. The opposite side length would be y, because this height here is y if this coordinate is x comma y. This adjacent side is x, again coming from the coordinate point. This is xy. And then the radius of the circle is r, and that's the hypotenuse of my right triangle. So now we can make the connection that the trigonometric functions that we previously defined as y over r is the same as opposite over hypotenuse if we consider this right triangle. And cosine theta was x over r, we get adjacent over hypotenuse. And tangent theta, y over x, is opposite over adjacent. So we're really just making a connection to the previous concept. And the reciprocal functions for cosecant, secant, and cotangent also apply. So in this example, given the following triangle, find the 6 trigonometric functions for theta. So here I have this triangle that's inscribed inside a circle. And I have the coordinate point that intersects the terminal side of the angle with the circle. So now I need to go ahead and find those side lengths of the triangle. Well, if I have this coordinate point here, that means that this adjacent side is the x value, 24. That's how much I move to the right. And then to move up to the coordinate point, I'd move up 7. So that's my opposite side in relation to my angle theta. So now I'm in need of my hypotenuse in this right triangle, and this is actually a common Pythagorean triple. So the common Pythagorean triples are provided here, or a few of them are provided here. So they're definitely worth memorizing so that we don't have to always work through the Pythagorean theorem. So if my two smaller side lengths are 7 and 24, that automatically makes the hypotenuse 25. So sine is opposite over hypotenuse, so 7 over 25. And I'll go ahead and right away find cosecant. That's the reciprocal, 25 over 7. For cosine, we have adjacent over hypotenuse, so 24 over 25. And secant will be the reciprocal, 25 over 24. And tangent, we have opposite over adjacent, 7 over 24. And then cotangent would then be 24 over 7. Special right triangles. Let's go and take a look at the first one. This one's called a 45-45-90 triangle based on its angles. And we want to focus on, we actually want to memorize the side lengths because they come up so frequently. So in a 45-45-90 triangle, the two smaller side lengths are going to be the same because it's an isosceles triangle. And if they have a length of 1, by the Pythagorean theorem, if we solve, that means that the hypotenuse has a length of radical 2. Now the other special right triangle is a 30-60-90 triangle, again based on its angles. Now for this right triangle, across from the 30-degree angle, we're going to go ahead and give that a length of 1. And across from the 60-degree angle, we have a length of the square root of 3. Then by the Pythagorean theorem, if we solve for the hypotenuse, we get out just 2. So all that's happening in this third triangle is looking at it from the 60-degree perspective instead. That across from 60 is radical 3, but the same thing was happening over here. It's just the perspective was that the 30-degree angle was in that bottom left corner. Now the 60-degree angle is in the bottom left corner. But still, opposite 60 degrees is radical 3, opposite 30 degrees is 1, and the hypotenuse is 2. So these special right triangles come up very often, as you will see. In this example, find the 6 trigonometric functions for an angle measuring 60 degrees. Well, we have our triangle here with an interior angle measure of 60 degrees in a right triangle. So I can go ahead and apply SOH-CAH-TOA. So if I want sine of 60 degrees, I go opposite over hypotenuse, radical 3 over a length of 2. So sine 60 is radical 3 over 2, meaning cosine 60 is 2 over radical 3, which is 2 radical 3 over 3. Cosine of 60, So cosine is adjacent over hypotenuse, so we have 1 over 2. And the reciprocal of that, 2 over 1, would simply be 2. And tangent of 60 is going to be opposite over adjacent. So we have opposite radical 3 over adjacent 1. So that's just radical 3. And if I take the reciprocal, it was radical 3 over 1. So that's 1 over radical 3, or radical 3 over 3. In this table, we have function values of special angles. So in degrees, our special angles are 30, 45, and 60. And then our functions are sine, cosine, tangent, cosecant, secant, and cotangent. So we, in other words, in the previous example, found these 6 values. So sine of 60 degrees was the square root of 3 over 2. Cosine of 60 degrees is 1/2. So this table gives the values for 45 degrees for all 6 trig functions, if I read across the row here, and for 30 degrees as well, if I go ahead and read across the row. So in this example, give the exact value of each expression. So part A, we have sine of 45 degrees plus cosine of 270 degrees. So sine of 45 degrees, we can go ahead and obtain the value from the table, or we can memorize it, or we could sketch a triangle. So for 45 degrees, I would go ahead and sketch the right triangle with 45 degrees is my interior angle. I know that the 2 smaller side lengths are 1, and the hypotenuse is the square root of 2. So sine of 45 degrees is opposite over hypotenuse. So I have 1 over the square root of 2. So go ahead and leave that at least for now. Plus, then we're going to go ahead and figure out cosine of 270 degrees. 270 degrees is a quadrantal angle. So I'm going to go ahead and come up here and sketch 270 degrees is down here, where the coordinate point would be 0, -1. Now cosine means that I'm looking for the x value, right? X over r, well that r is 1. The x value is 0, so cosine of 270 degrees is 0. So here I'm adding these together, so 1 over rad 2 plus 0, that's just 1 over rad 2. If I rationalize, I get the square root of 2 over 2. For part B, I'm looking at secant 60 degrees minus cosine -180 degrees. So let's start with secant of 60 degrees. And the first thing I'm going to do is rewrite that as 1 over cosine of 60 degrees. So I'd much rather deal with sine, cosine, and tangent. I have SOH-CAH-TOA than their reciprocal functions. So first I'm going to evaluate cosine of 60 degrees. And again, I can memorize that value, or I can go ahead and draw myself a triangle with that interior angle of 60 degrees. And then I have to know the side lengths, my special right triangle. So opposite 60 degrees is the square root of 3. Opposite 30 degrees is 1. And the hypotenuse is 2. So cosine of 60 is going to be adjacent over hypotenuse, so 1/2. So I have 1 over 1/2, which is just 2. And then I'll move on and evaluate cosine of -180 degrees. So we have another quadrantal angle, -180 degrees. Well, that's going to take me in this counterclockwise direction. So my coordinate point over here would be at -1, 0. Cosine, again, is looking for the x value. So I have -1. So here I have minus -1. That's plus 1. So we have 2 plus 1 is 3. So for part C, tangent squared of 60 degrees plus sine of 30 degrees. So first I'm going to rewrite this as tangent of 60 degrees squared plus sine of 30 degrees. So I'm looking for tangent of 60 and sine of 30 degrees. So I'm going to go ahead and draw just one triangle actually, because I have a 30, 60, 90 triangle, even though this looks like a 45, 45, 90. Sorry about that. We'll just go ahead and call it a 30, 60, 90. So across from 60 degrees is the square root of 3, across from 30 degrees is 1, and the hypotenuse has a length of 2. So for tangent of 60 degrees, we're going to focus on the 60 degree angle. So tangent is opposite over adjacent. So opposite 60 degrees is radical 3, and adjacent is 1. So that means that tangent of 60, that's radical 3 over 1, so that's radical 3, and then that quantity is squared. Now for sine of 30 degrees, I'm going to go ahead and focus on the 30 degree angle this time. So sine of 30 degrees, sine is opposite. So opposite 30 degrees is 1 over hypotenuse. Well, the hypotenuse is directly across from the 90 degree angle. That's 2. So sine of 30 is opposite 1 over hypotenuse 2. So I have plus 1/2. So the square root of 3 squared, that's 3, plus 1/2, that's 3.5 as a decimal, or you can leave your answer as a fraction 7 over 2 as an improper fraction. Finally, for part D, I have cotangent of 45 degrees minus sine of 90 degrees. So instead of dealing with cotangent, I'm going to go ahead and write this as 1 over tangent of 45 degrees. So I need my 45 degree triangle, and my 45 degree right triangle has side lengths 1 and 1 and a hypotenuse length of radical 2. So tangent of 45 is opposite over adjacent. So that's 1 over 1. It's really nice. So I get 1 over 1 over 1. So 1 over 1. And then we need to do minus sine of 90 degrees. Well, 90 degrees is a quadrantal angle. So if I think about where 90 degrees is on the positive y-axis, my coordinate point there would be 0, 1. And sine is looking for the y value, so sine of 90 is simply 1. So I have minus 1, so I have 1 minus 1, which is just 0. Special right triangle with hypotenuse length 1. So here's one of our special right triangles. The hypotenuse length is 2. And an ideal situation would be to have a hypotenuse length of 1. So we're just simply going to take every side length and divide by 2. So if we do that, then my hypotenuse has a length of 1. And then my side that's opposite 30 degrees is 1/2. And my side that's opposite 60 degrees is radical 3 over 2. So now I have this hypotenuse length of 1, which corresponds to having a radius of 1. So here are all our special right triangles on a circle with radius 1. So we already saw the 30 degree angle, so now we have the 45 degree angle with a radius of 1. So we have our two side lengths are radical 2 over 2 and radical 2 over 2. And here our 60 degree angle is going to have the opposite side is radical 3 over 2 to 60 degrees, and opposite 30 is 1/2, so that the hypotenuse is 1. How function values change as angles change in quadrant 1. So we're interested in how the trig functions change as my angle moves from 0 degrees all the way up to 90 degrees. So we'll focus on the trig function sine. So let's go and take a look at this first triangle here corresponding to an angle of 30 degrees. If we focus on the sine value, that's the y value. So I'm looking at this first height here, and that would correspond to a y value of 1/2. As I move to an angle of 45 degrees, I'm looking at the y value. So that y value has grown to the square root of 2 over 2. And as I move to 60 degrees, I can see that y value is the height of my triangle, and that y value becomes radical 3 over 2. So each of those heights, each of those y values was getting bigger as my angle increased. So as theta increases from 0 degrees to 90 degrees, sine of theta increases as well. Now let's think about what's happening to the cosine function as our angles increase. So we'll start with an angle of 30 degrees. So if I look at this triangle here, if I think about the x value, so the x value would extend all the way out here. So I'm looking at this distance that corresponds to radical 3 over 2. And then I would go ahead and look at what happens at 45 degrees. So I'm looking at this triangle here. So that x value would now be here. So this is the x value that I'm talking about. So that's exactly radical 2 over 2. And then finally, the last triangle we're going to look at, the 60-degree angle. So the x value that we're focusing on for cosine is even smaller. So it is exactly 1/2. So as my angles increased, my cosine values, my x values decrease. So as theta increases from 0 degrees to 90 degrees, cosine theta decreases. So now let's look what happens to all the rest of the trig functions. So tangent theta, which is the ratio of sine over cosine, increases because sine's getting bigger, but cosine's getting smaller. So the numerator is a bigger number than the denominator. That means that my ratio is increasing. So then now for cosecant, secant, and cotangent, it's just the opposite of the reciprocal. So sine increases, but its reciprocal, cosecant, decreases. We said cosine decreases, so its reciprocal, secant, increases. And then we just said tangent increases, so cotangent, its reciprocal, decreases. In this example, let's determine whether each statement is true or false. Is sine of 21 degrees greater than sine of 18 degrees? So we're referencing what we just talked about. So since 21 degrees is greater than 18 degrees, we know that sine is getting bigger and bigger the bigger angles that you plug into it. Sine is increasing as you plug in bigger and bigger angles. So that means that this is a true statement. Sine of 21 would be bigger than sine of 18 degrees. So the first statement is true. The next statement, I'm looking at secant of 56 degrees is less than or equal to secant of 49 degrees. So we can use the comparison. We can go over here and think about what we covered. But the other option would be I can, instead of thinking about secant, take the reciprocal. So I can think about cosine of 56 degrees instead, but I'd have to flip the inequality. Is greater than or equal to cosine of 49 degrees. So now here, is cosine of 56 degrees going to be bigger, greater than cosine of 49 degrees? And the answer there is false. So we know as we plug bigger angles into cosine, cosine actually starts getting smaller. Those x values start to shrink. So this statement is false. And then finally, is tangent of 72 degrees less than tangent of 65 degrees? So we said that tangent, as we plugged in bigger angles, did actually get bigger and bigger. So 72 degrees is a bigger angle than 65 degrees, so this quantity on the left would have to be bigger, not less than. So this is false as well. And that was without ever determining these exact trigonometric function values for these respective angles, because notice, none of these are really nice angles that we can work with, like 30, 45, or 60. Cofunction identities. For any acute angle A, the following relationships hold. Sine of A is equal to evaluating cosine of 90 degrees minus A. And cosine A is equal to doing sine of 90 degrees minus A. So we say sine and cosine are cofunctions of one another. Similarly, tangent and cotangent are cofunctions of one another. So instead of doing tangent A, we can do cotangent of 90 minus A. And then secant and cosecant are cofunctions of one another. So instead of evaluating secant A, we can evaluate cosecant of 90 degrees minus A. Write each function in terms of its cofunction. So first we have cosine of 52 degrees. So we go to its cofunction, the sine function, and we write sine of 90 degrees minus 52 degrees. So it's the same as sine of 38 degrees. For tangent, we go to its cofunction, cotangent, of 90 degrees minus 71 degrees. So we have cotangent of 19 degrees. And then secant and cosecant are cofunctions. So we have cosecant of 90 degrees minus 24 degrees. So cosecant of 66 degrees. In this example, we want to find one solution for each equation. Assume all angles are acute. So here's what we have. We have an equation. We have cosine of theta plus 4 degrees equals sine of 3 theta plus 2 degrees. So we want one angle theta that we would substitute in that would make these two trig functions the same, equivalent. Now, the problem is that this is a cosine function and this is a sine function. So we can't just set their two insides equal to each other and kind of drop the trig function because they're not the same. But we can write one in terms of its cofunction and then they'll be the same. So I'm going to go ahead and leave cosine theta plus 4 degrees alone, but I'm going to rewrite the right-hand side as cosine of 90 minus parentheses 3 theta plus 2 degrees. So I'm rewriting sine in terms of its cofunction cosine by doing 90 degrees minus the angle. Well, I have to keep parentheses around this whole quantity. So now I have cosine of theta plus 4 degrees is equal to cosine of 90 degrees minus 3 theta minus 2 degrees because that negative will distribute. Or cosine of theta plus 4 degrees equals cosine of 88 degrees minus 3 theta. So now that they're the same trig function, the only way the left side can equal the right side is if their inside is the same, which is formally called the argument. So if I set theta plus 4 degrees equal to 88 minus 3 theta and solve for theta, I will get the value I'm searching for. So theta plus 4 degrees has to equal 88 degrees minus 3 theta. And I want to be clear about something here. We are not dividing by cosine. So we can't divide by just this COS. That doesn't make sense. So we're recognizing the only way these two can be equal is if their arguments are equal. So we're extracting those and setting those equal to one another. So if I add the 3 theta to the other side, I get 4 theta is equal to, if I subtract 4, I get 84 degrees. So theta is equal to 21 degrees. And for part B, we're going to solve this equation in a very similar way, except we have tangent and cotangent. They too are cofunctions of one another. So we'll go ahead and rewrite cotangent as its cofunction. So here we have 90 minus parentheses theta plus 18 degrees, and then we'll distribute, and then combine like terms. And now that we have the same trig function tangent, we can set their arguments equal to one another, and then solve. So add theta to the other side, I get 3 theta, add 18 to the other side, I get 90. So this time my theta value is 30 degrees.